Okay, so yeah, my interest in this subject is the essentially the physical origin of the quantum effects. So it's already been said a couple of times. Then this may well help a lot in trying to understand all of the issues and the meaning of things. So I work from a sort of simple point of view that there are observed quantum properties, the E equals h bar omega quantization, electron quantization, wave functions, uncertainty principles. These are measured properties, and so they must originate from the properties of something. And at this point, I think quantum theory doesn't identify what that something is. So, you look at, for example, quantum electrodynamics, which of course describes everything very nicely, but it assumes quantization. It doesn't derive it. All the other equations of quantum mechanics, Schrödinger, Dirac, they describe the quantum properties, but they don't attribute them to a physical origin. And you can't discern that physical origin easily by just looking at the equations. I put in an archive reference which describes this in a little more detail. So, I mean, maybe everybody believes there has to be a physical origin, but there are some arguments for that case. So again, you can say the E equals h bar relationship is not a property of electromagnetism as we know it. It's just added onto it with no obvious origin. And similarly, the electron wave function. Maybe it's a property of the electron, but it doesn't seem very likely. The electron's a point particle. The wave function is extended. It's an added property that doesn't obviously come directly from the electron. Going on. Planck's constant, all of the constants of physics, relate to some physical entity. And so the fact that quantum mechanics introduces a fundamental constant assumes that it's the property or related to some physical entity. And then another thing to say is that the relationship equals h bar omega. So it applies to electromagnetic waves. It also applies to phonons, which are sort of mechanical vibrations of a cluster of atoms, and through the de Broglie relation, it applies to elementary particles. So you have the same law applying to, what are, completely different physical objects. And so it just leads to the notion that there is something underlying all of these things, some common origin that provides these properties. So, and the problem, of course, is, what could that possibly be? And as we know, there are no fields that are introduced in quantum mechanics. There are no particles. So, that's not the source of the physical origin. It just seems as if all of the aspects of classical mechanics suddenly take on another property, which doesn't have an obvious origin. So it occurred to me that one way out of this is to say, well, is it possible that some component of, if you like, classical mechanics, which we don't normally expect to have physical properties of its own, actually does have physical properties? And if you look at the characteristics of mechanics, which might be momentum, position, mass, or not mass, but and so on and so on, the only thing that seems to be a viable option is energy. So it seemed to me it was worth exploring the question of, if you take the point of view that energy is not what is normally thought of as just a quantity describing a state, is actually a physical object therefore has some physical properties. And the notion is that that energy state, has to be combined with particles or radiations and so on to provide a full system of the system, and that the properties of the energy state, imbue the whole system with the quantum properties. So to take that along a bit further to see what this means, look to start with at the quantum effects of particles. And this is all a qualitative description, because the equations of quantum mechanics we know are right, and so they describe all of this. It's a question of, does this notion of having energy as a physical object make qualitative sense in the description? And so what this sort of brings in is, now when you describe, say, an electron, you're not describing one object, you're actually describing two objects. One is the particle, the electron, or whatever else, and the second is energy. And it's pretty clear that within this description, energy is providing the wave-like aspect of things, the wave function, the E equals h bar omega description. And so we see this as saying the wave function is a property of the energy state. And this little diagram up here in the corner, which I hope you can see, sort of shows the combination that there is, an energy state, which is essentially represented by the wave function, and within it, a particle. And it's the two together that provide the description of the system and the quantum mechanical properties. So if we just look at the various sort of aspects of quantum mechanics, starting from the simplest one, wave-particle duality, has been sort of thought of as a dichotomy, something that seems to be one thing and sometimes seems to be the other. But you can say, well, now we have, a particle, is described by this combination of two physical objects, one of which is the particle, one of which is the wave. And so this is the wave-particle duality is just a sort of natural description of the physical situation. And then if you look at sort of measurements, we're now talking about measuring two different things. And any particular measurement will only measure one of them. So if you measure the electron, energy, or momentum, or velocity, or one of the things related to it, you're measuring the energy state. You're not measuring the particle directly, and vice versa. If you measure the particle directly, you're not measuring the energy state. And so it is this fact of having two physical objects present, only one of which you're measuring, gives the probabilistic sort of Copenhagen type of interpretation and the uncertainty principle, because there is no way of measuring both at once. And so if you measure the energy, you can only deduce the property of the particle indirectly as being somewhere within the envelope of the energy state. And so that leads to naturally to a probabilistic interpretation. So things like the two-slit diffraction, it's the energy wave that is diffracting, not the particle. So I know that there's been a lot of discussion of the two-slit measurement, and if in the situation that the wave function simply represents the electron, then since the wave function has to go through both slits for the result to happen, one ends up with the conclusion that the electron has to go through both slits, not just one or the other, and that's a problem. So this scheme of having these two properties together gets over that, because it's the energy goes through both slits. The particle doesn't have to. So the next step is looking at quantized states. Again, something in quantum mechanics that doesn't have a very obvious reason why the energy level should be quantized. But now we have a situation where the system is described by two different physical objects which have two different sets of properties. And so the allowed states have to be consistent with both of them. So my little schematic there says, there's a space of, the Coulomb energy states, basically an infinite number of possible states. And then there's another space of possible energy states. But it's only where those two overlap, the intersection of the two things, which is an allowed state. And that then reduces the number of possible solutions down to a few, the quantized states. And so, just to give a sort of an analogy. So, there's a lot of situations in physics where, let's take, for example, heat diffusion. So the heat diffusion equation, allows an infinite number of solutions. But when you provide boundary conditions to it, those solutions reduce to just one. And so, the same thing is happening here. It's the fact that there's these two physical entities that are combining, constrains the solutions down to a small number, and those are just the quantized states. And if you look at the Schrödinger equation, this is basically what it's describing. The Schrödinger equation is an equation of energy, sort of kinetic energy plus potential energy is energy. It contains the Coulomb term, and it contains the energy term. And so, you can look at the Schrödinger equation and say this is just what it does. It's looking at the sort of the intersection of the energy states and the Coulomb states to give the quantized states. So next, the Dirac equation comes up with negative energy. So, if you think of energy in the usual way, it has to be, positive, definite. It's basically impossible to understand a negative energy if it has its conventional meaning. But once you allow energy to have physical properties, then there is no reason why it shouldn't have positive or negative energies. So, for example, consider electric charge. Nobody particularly would worry about the fact that there is both positive and negative charge. It's simply a property of charge. And so once you imbue energy with as a physical state with physical properties, it can have positive and negative values. And they have some physical meaning to them, and that associates with matter and antimatter. Oh, and if we look at again photons and phonons, so the relationship E equals h bar omega, is a property of energy, and just the equation is basically sort of you look at it and say, well, it's obviously that's how you would interpret it. It's describing saying energy, is a wave proportional to omega with a fundamental constant giving its relationship and size. So it is an added constraint on the energy of an electromagnetic wave because the energy of the wave has to support the properties of energy. And then this also explains why any oscillation obeys the same relationship. So it's as we said, electromagnetic waves and phonons, lattice vibrations are just fundamentally different physics, but the common element, in fact the only common element, is energy. And so if you now allow that E equals h bar omega as a property of energy, it's very simple to understand that it would give you the same quantization law for oscillations of any types. And then phonons, it was actually sort of the phonons that sort of ended up convincing me that this has to be right, because phonons are a collective excitation of many atoms. It can be a few, it can be an infinite number, and it's just hard to see what could possibly be how properties of the individual particles could combine to quantize a phonon. And basically the only collective property of a phonon a lattice vibration is energy. So if it's quantized, it sort of has to be a property of energy. So that's the sum of this. So to summarize, I mean, the proposal here is that energy, is a real physical construct, entity. I'm not sure what a good word for it is, and it is the properties of energy that provide the basis for understanding quantum mechanics. I think I'm trying to make the case that qualitatively it describes the quantum effects in a way that seems to me rather sort of straightforward and understandable. It seems consistent with quantum theory, and I mean, clearly this is what quantum theory is describing. I mean, I think we don't previously, what quantum theory describes has been not so clear, but what I would say is that what quantum theory is describing is the property of energy, the properties of energy as they apply to the various situations, particles, waves, so on. And so, to some extent, the sort of mysteries here, can be replaced with physical properties. And, this is sort of, I think, the way the rest of physics works. We may not know why a physical entity exists, but if you can describe it with its properties, then it makes the result of that physical entity a little clearer. And so, from all of this, the energy state, seems to be, or was the description of it through the quantum mechanics, is that it is spatially extended and it's wave-like, and its properties, are constraining, all energetic excitations and providing the quantum properties. And then, so Planck's constant would then be the magnitude of this sort of fundamental energy state. So yeah, that's what I had to say. I'm interested in any comments.
Thank you very much. And I ask everyone to turn on the microphones, so you can ask Dr. Street questions, please.
How would you compare your idea of energy with something like Bohm's notion of a quantum potential, which also have that there's like spatially extended aspect with a discrete particle in interaction with it?
Good question. I mean, the Bohm idea of a pilot wave seems to be one thing that is sort of closest to this, in the sense that it sort of views the wave as essentially a real thing. I don't know if it said what that real thing was, but I'd say it's sort of closer to this point of view than other aspects, other interpretations which view the wave function as not a real thing, just sort of representational, if that makes any sense.
Okay.
I guess there's no more questions. So thank you very much, Dr. Street, for your presentation.